So our next installment, 6.7, we are looking at sticky collisions. And what is also true in these cases, because it is always true everywhere at all times in the universe, is the initial momentum of a system equals the final momentum of a system, the law of conservation of momentum. So what we're talking about when we have a sticky collision is, if we look up at our diagram at the top, we see again we have interaction of particles, explosions, collisions, bouncy collisions, and in this installment we're looking at sticky collisions. So what this looks like in real life is we might have a situation where we have a cart like this, and it's at rest. It actually doesn't matter whether it's at rest or not, but to simply understand it, we'll consider the first case of it being at rest. And we have like some kind of, let's say, a bullet that is fired at this cart. Well, then afterward, that cart gets hit by that bullet, and that bullet embeds itself in the cart, and now the two move off together. So what's happening in this case is that the initial momentum of the system is all in the bullet, and when it hits the cart, the momentum is shared. And if P equals mv, we now have a greater mass that is sharing the same momentum, which means the velocity should decrease. So let's use our law of conservation momentum formulas to do some accounting here. We got our initial equals final, and beforehand we have two particles. And afterward we have one particle, and that's what's changed here. What makes this unique is we have one particle. They've stuck together. So we now have this particle 1, 2, which is the sum of the other two. So we get m1 v1 plus m2 v2. And this is going to be m12 v12. But this m12 is really m1 plus m2. Or the v12, excuse me. So what we have now is this second particle has the combined mass. And that is the interesting property. If we were looking for v12, then it would be that relationship where we're dividing both sides by the sum of the masses m1 plus m2. So this is what we're looking at here, and if we are looking to predict the final velocity, we're looking at that there. So let's try a concrete example here. And let's do a sticky collision. So we've got our time 0 and our time afterward. We've got a box car coasting on the tracks at 4 meters per second. It collides with two identical coupled rail cars moving the opposite direction at 2.5 meters per second. So what we have, the other particle, is there are two cars that are already together, and they're moving in this direction at 2.5 meters per second. Now that's a negative because our positive direction is to the right and our negative direction like so. So afterward, what we have is we have three carts stuck together, behaving as one. And the question is the velocity in this direction? Is the velocity in the other direction? So we'll do our accounting. P0 equals the instantaneous momentum, and beforehand we have two particles. This may seem confusing, even though this is made of two carts, it's treated as one object because it's basically one object. This cart itself is made up of 4 wheels and a body, but we consider it one object. It's made up of 10 to the 30th atoms, but we consider it one body because it's operating and functioning as one body. So these two operate as one body. And then afterward, we only have this combined object. So we've got m1 v1 plus m2 v2 is going to equal m12 v12. And that mass is going to be m1 plus m2 times the v12. And what we're looking for is this velocity. So we're going to divide both sides by m1 plus m2. That drops out, and then we're looking at that relationship. So now we can plug in the mass of the first object, which is 2 times 10 to the 4th, times its velocity, which is 4. And the second object, which has the equivalent of 2 of those, so that's 4 times 10 to the 4th, times negative 2.5. All over, in the end, 6 times 10 to the 4th. Now what you may see here is that these 10 to the 4th, because they're in every term, can be crossed out. If we had factored out that 10 to the 4th, we'd have a 10 to the 4th outside in the numerator, and that would cancel with the 10 to the 4th at the bottom. So what we're left with then is we're left with 2 times 4, which is 8, plus 4 times minus 2.5, which is minus 10 all over 6. And that is going to be minus 2 over 6, or minus 1/3 meters per second. And notice it's a negative, so that means the whole thing will be moving to the left at minus 0.33, repeating, meters per second. Now, why should that be? If we look at the momentum initially, we have 4 meters per second times 1 mass unit, which is 4, plus 4. And on the other side, we have 2 mass units times minus 2.5. So that gives us minus 5. So notice that the momentum is negative. The total momentum beforehand is negative. So the total momentum afterward would be negative, which means that it will end up having a negative velocity. So we could predict the direction of the velocity right off the bat by just determining which of these two has a larger momentum, because it will win. It'll win out in that case. And we could go through and do the check, and it works out as well. So this is an example of a sticky collision.